All right, the basics of charge. So the history of charge. Charges break down into one of two categories. You have charge that's produced by rubbing plastic or vinyl. So over here, I got a PVC pipe. So here we have plastic. If you rub plastic like this generates one type of charge versus rubbing a glass rod that generates another type of charge. It was Ben Franklin who named these charges positive and negative, and it was totally an arbitrary choice. I don't know if you realize that. What we call positive and what we call negative, back in the 1700s, Ben Franklin literally was like, let's call the charge that I get from rubbing glass, let's call that positive. Let's call charge that I get from rubbing, well, it wasn't plastic, it was actually what I call amber, which is petrified tree resin. You rub amber and that generates another type of charge. He called that negative. So as you're well aware, what we know is that unlike charges attract and like charges repel, which is what this diagram here is showing. So if you have a negative object and another negative object is brought near it, what's going to happen if you have two negative objects? They're going to push away. So that's what this arrow right here is showing. This arrow is showing that this ruler that's hanging from a thread, this ruler is going to move away from this other negative object because like charges repel each other. And then same thing in this diagram. We have a glass rod that's been positively charged. This other glass rod that's positive is brought near to it, and the positive glass rod that's hanging from a thread moves away. Like charges repel. And then the last one, we have the negative ruler and the positive rod, and what's going to happen there? They're going to attract. Now I learned a new word reading the textbook last night. So this right here, this scale, this is referred to as the triboelectric scale. Anybody know the prefix tribo? There's a prefix that, does anybody know? Tribo means, it's the Greek word for rub. So it's the scale, like what happens when you rub things. So, and then interestingly, I don't have an answer for this, air. Air is at the top of the scale. How do you rub air? I don't know. Okay, the human body. You rub the human body, what's going to happen? Positive or negative? Positive. Glass is high on the list. Okay, positive. And down here you get your plastics, vinyl. What I have hanging over here, this is a piece of vinyl right there. Vinyl, when rubbed, is going to become negative. Typically speaking. Okay, that's the basics of charge. Now, getting a little more specific. Okay, the anatomy of the atom. So most of you know this. So in the center of the atom we have, what's it called?
Nucleus.
The nucleus. We have the nucleus, and what is the nucleus made up of?
Neutrons and protons.
Protons and neutrons. So the proton has a positive charge. The neutron as a whole is no charge. And then the electron is negative. So we have protons, neutrons, electrons. So here's what you need to know. The absolute value of the charge of a proton is equal to the absolute value of the charge of an electron. The charge of a proton and the charge of an electron, it's the exact same charge, well, other than the fact that they're equal and opposite, proton being positive, electron being negative. Now, what most of you don't know, in fact, I would say all of you don't know, even if you took AP Chemistry, even AP Chem kids don't know this, is there is an actual value for the charge of the proton and the charge of the electron, and it is this number right here, 1.6 times 10 to the negative 19. Now, what is C?
Coulomb.
C is the Coulomb. How many of you have heard of the Coulomb before? Okay, the Coulomb is the base unit of charge. It's what we measure charge in. It would be like this. What's the base unit for mass? What do we measure mass in? Kilograms. What do we measure length in? Meters. What do we measure time in? Seconds. What do we measure charge in? Coulombs. So we abbreviate that C. So the charge of a proton, charge of an electron is 1.6 times 10 to the negative 19 coulombs. We refer to this number as being an elementary charge. So why would we call this an elementary charge? Well, my kids are all in, my kids are in elementary school. What does that mean to be in elementary school? You learn the basics. It's the fundamentals, right? So if you're talking about charge, the thing to know is that charge comes in bundles of this amount right here. This is the building block. This value of 1.6 times 10 to the negative 19 coulombs, that's the building block of all charge. So what's the very first possible charge you could have? 0 coulombs. What's the next biggest charge you could have? After 0 coulombs, what's the next biggest? 1.6 times 10 to the negative 19 coulombs. What's the next biggest? 3.2 times 10 to the negative 19 coulombs. The next biggest, 4.8 times 10 to the negative 19 coulombs, like that. Nothing in between, right? It comes in units of that value. Okay, second thing to know. Protons, when in the atom, the protons are held very tightly, especially amongst solids. All right, so protons are not free to move. Now, number 3, in conductors, electrons are loosely held. So what's the implication of that? Well, if electrons can move around, they are going to be the ones that explain atoms becoming charged. If you have an atom that suddenly goes from being neutral to being negatively charged, what's going to be the explanation? Was there a movement of protons or was there a movement of electrons? Electrons. Protons don't move. Protons stay fixed in the nucleus. Okay, so in conductors, electrons are loosely held in the atom. They're free to move around. Okay, last on this list, the net charge of an atom is determined by the number of protons and the number of electrons. So, for example, if you have a neutral atom, what does that mean? The number of protons and the number of electrons will be the same. Protons and electrons are the same. If you have, thanks for doing it off. Thank you. She's doing all my work for me. If you have a positive ion, oh, and I should mention, what is an ion? You should know the word ion. What is an ion? A charged particle. It's a charged atom. A positive ion is where you have more protons than electrons. And a negative ion is where there's more electrons than protons. So think of an atom becoming charged. It's like a battle between the protons and the electrons. But at the end of the day, what's going to be doing the movement? Will the protons be moving around to charge the atom, or will the electrons be moving around to charge the atom? The electrons. The electrons. So that's what I wrote right here. The electrons are what move when atoms become charged. All right, any questions here? It gets better. We're moving on. Okay, the law of conservation of electric charge. Now, there's other conservation laws that you guys know. So if you took AP Physics 1, you know the law of conservation of energy, right? What is the law of conservation of energy state? Energy.
Oh, wait.
Energy cannot be created or destroyed. It simply moves from one form to another. Okay, what are some other conservation laws you know? Conservation of mass. Dude, mass cannot be created or destroyed. It moves from one form to another. You can't create new mass and you can't destroy mass. Now, the same logic applies to charge. The law of conservation of electric charge. Here's what this law says. Charge cannot be created or destroyed. Or another way of saying that, it's the exact same thing. The net, the total charge produced in any process is 0. You're not creating new charge and you're not destroying charge. So here's an example. So we have a balloon with a cloth. And if you look carefully at this diagram, notice that there's the same number of pluses as minuses. So how many pluses are on this balloon?
5.
5 pluses and 5 minuses. What's the total charge on the balloon? 0. Okay, if you look at this cloth, I haven't done it yet, but let's see. So we got plus, 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 plus. How many pluses are they showing us? 1, 2, 3, 4, looks like 8, 9, 10?
I see that. Forgot there's another one.
But
Okay, there's 10.
Okay, but if you count them up, total positive equals total negative. What's the total charge on this cloth?
0.
0. Now, here's what happens, as we've already said. If you take like a rubber balloon, or here I have a PVC pipe in my hand. If you take a cloth and a pipe and you rub the pipe, am I generating new charge?
No, you're just moving the charge
No.
from the cloth to PVC or vice versa.
What's happening is this. So if the balloon, so here in the diagram we have a balloon. Notice now, if you look over here after rubbing, notice that the balloon, does it have more positive or more negative?
More negative.
It's more negative. The balloon has become negatively charged. The cloth has become positively charged. Now, what would explain this? Well, when you take the balloon and rub it with a cloth, what's happening there? Electrons are moving from the cloth onto the balloon. Electrons are moving from cloth onto the balloon. Did we generate new charge?
No.
No. What is the total charge? What was the total charge before rubbing?
0, 0.
The total charge over here was what? 0 coulombs. What's going to be the total charge over here?
1.
0.
Oh, you're right.
Right? Total charge before equals total charge minus. The total negative must equal the total positive. You're not going to be creating new charge as a result of rubbing the balloon. Does this concept make sense? All that happens is electrons left the cloth, went to the balloon, so therefore the cloth was left positively charged, the balloon became negatively charged. Charge is not created or destroyed, it simply moves from one place to the next. All right. Okay. Insulators and conductors. I think everybody has a general idea of this. What do we mean by an insulator? An insulator is something that does not allow electrons to move freely. The electrons in an insulator are held tightly to the nucleus and not free to move about. Now, what is a conductor? A conductor, the electrons in a conductor are not held tightly and they're free to move. So what are some examples of insulators? Yo. Well, no, charges can move through a resistor, but there's a lot of resist. Yeah, you know what? There is a. That's a good question. Yo.
Rubber.
Rubber is definitely an insulator. Dude, I got to think about what you just said. I do. A resistor. I mean, charges do move through it, but there is resistance there. Okay, what else is an insulator? Wood. What else? Plastic. Plastic does not conduct electricity. Okay, what are good conductors? Well, actually, water does not conduct electricity. Do you want to know what conducts the electricity?
Ions.
The ions that are within water. So it's got it, like if you had pure water with no ions in it, it would not conduct electricity. What conducts electricity are the ions within the water. Metals. Pretty much all metals are good conductors. Right? So looking down here, so look, we have, this is a good example of the law of conservation of charge as well. So here what we have, so count up the positives on this positive dude. How many positives are there? 6. So let's just say that our starting charge, these two combined right here, the starting charge is plus 6, and let's say that's like microcoulombs or something. Okay, now if you have a conductor, if you connect these two spheres together with a conductor, my first question is, which way are the electrons going to move in the conductor? When you put a piece of metal right here, you're putting a piece of metal across these two spheres. which way are the electrons going to move in that conductor? From left to right or right to left? The electrons are going to move inside this metal. The electrons are going to be moving right to left, right? The negative charges that are in here, are going to move to the left. They're going to be attracted to the positive. Now, when these electrons move to the left, that's going to leave this sphere positive. That's why that sphere becomes plus, right? Now, notice, what's our total positive here? We have plus 3. We have 1, 2, 3. How about on this sphere? 1, 2, 3. So what's our total charge on this guy for this whole situation here? What's the net charge there? Plus 6, right? All right, then this last one, we have a conductor. I'm sorry, an insulator. Will any charges move through the wood? No, so it stays the same as the beginning, right? But the total charge is still plus 6 microcoulombs. All right, 3 ways to charge an object. You can charge an object by rubbing, as we've said. You can charge an object with conduction, and you can charge an object with by induction with a ground. So rubbing, we've already talked about. Typically, if you rub an object, it's either going to become positively charged or negatively charged, depending where it is on the triboelectric series. Conduction. So conduction, the key thing is it involves physical contact. Physical contact for conduction. I don't have anybody's homework. Yeah, sorry.
Okay, thank you.
Okay, so conduction. So here we have a neutral metal rod. Okay, neutral metal rod. Now we have this charged rod. If this charged rod here is brought in and touches the neutral rod, if you bring a positive rod to the neutral rod, which way are electrons going to move? When this contact is made right here, which way are the electrons going to move? The electrons, are they going to move from the positive rod down into the neutral rod? Or will electrons move from the neutral rod up into the positive rod? What do you think? Neutral rod and the positive rod, because electrons are negative. This rod here is positive, so the electrons are attracted up into this positive rod. Now, when these electrons do go up into this positive rod, what's that going to leave this rod? The neutral rod, once the electrons leave, the neutral rod is now going to be what? Positive. If electrons leave that rod will become positively charged. So that is charging by conduction. Make sense? Physical contact. Which way do the electrons move? Okay, now, induction. Charging by induction. So again, we have a neutral rod. Now the thing to know for induction is no physical contact. How do you spell physical? P-H-Y? Physical contact. No physical contact. So you have this rod here that's neutral. In fact, let's not show what happens yet. They're giving us the answer. Take that away, take that away. Okay, so it's completely neutral. You bring in this positive rod here without touching. What's going to happen to the electrons that are in this neutral rod? When this positive rod comes nearby, all these electrons that are in the neutral rod, which way are they going to be pulled? They're going to be pulled to the left. Now what's that going to do? If the electrons are all pulled towards the positive rod, what that's going to do is it's going to create a charge separation. So you get this region of negative and this region of positive, like that. Now is that permanently charged? Because what happens once this rod, once you take this rod and pull it away, what's going to happen to the neutral rod? It's going to go back to being, you know, not charged in any place. So I guess what I'm trying to say is this. When you have induction alone, did we provide a net charge to this neutral rod? Was there a net charge provided to it? No. All that happened is that we separated the charge. In fact, what does this say right here? The text here says, the metal rod is still neutral, but with a separation of charge. All that happened is the electrons went over here, which made this side negative and that side positive. There was no net charge given to the rod. So can you use induction to give the rod a true net charge? The answer is yes. How do you do it? So what I've talked about was induction. So to give this rod a true charge, we need induction with a what? With a ground. Now, what is a ground? A ground is a connection to the earth, right? Having a ground, it's a connection to the earth. Now, what's the significance of the earth? The earth is like a giant reservoir of charge. Can the earth conduct electricity? Yes, it can. Can the earth provide electrons or receive electrons? Yeah. So here's how you designate the ground. And we're almost done. Okay, so the way you put a ground in is like this. So what this represents is a connection to the earth. This symbol right here indicates grounding. Now, follow me. If you bring in this positive rod, no touching, this is induction. You bring in this positive rod like this, is this going to pull electrons up from the earth, or is it going to push electrons down into the earth? So we're bringing a positive rod near to this neutral rod. Is this positive rod, is it going to pull electrons up from the earth, or the other option is it going to take electrons from this rod and push them down into the earth? Which way is it going to go? Up or down? Up. Because look, it's like this. The electrons that are down here in the earth. Okay, so let's make this rod here completely neutral. Let's make it totally neutral. So there's like no separation. Electrons down in the earth are going to be pulled up because this rod is positive, right? Electrons are negative. If that rod is positive, that positive charge is going to attract electrons from the ground. So all these electrons are going to come streaming up from the ground. These electrons are going to come up like this, and they're going to go into this rod. Okay? Now, did that make the rod positive or negative? Negative, and then if you want to maintain that negative charge, you disconnect the ground. You literally cut the cable. Cut the cable, and now this rod will be negatively charged. And I guess one other way you could do it without a ground, if you really wanted to do it without a ground, what you could do is you could induce this separation of charge and literally break this. If you broke this into two separate pieces, like grab this right here, boom, he goes here, boom, he goes, or stays there or whatever, right? So this guy would be left negative, and then this guy would be positive. If you do induction and then break it, you'll have two separate charges. Okay? So in summation, conduction requires physical contact. The electrons are going to move towards the positive. Induction is no physical contact, and typically if you want to generate a new charge as opposed to just a separation of charge, if you want to do that, then you need to include a ground like this. Okay, final thing. The electroscope. All right, how long have I been talking?
20 minutes, 25.
Oh, this is longer than I thought. Okay, let me explain the electroscope and then we're done. Okay, what the electroscope is it's a device used for detecting charge, and it's really pretty simple to understand. So here is an electroscope. This is an electroscope, very fragile, okay? You don't want to be like poking around on it too hard. Okay, and then this is also an electroscope. There's two different styles of electroscope right here. Now, here's how it works. If you bring a rod up to this electroscope, so this is metal right here, this is metal, the metal goes all the way through and then down into here. These are metal foil. All right, so if this rod is, so pick one, plus or minus, doesn't matter. Let's say it's a positively charged rod. So here we have a positively charged rod like this. Now what is that going to do? What is that going to do to this metal ball? What's it going to do to the electrons in the electroscope? It's going to attract it. So electrons all throughout this metal, okay? All throughout this metal, electrons are going to be attracted up to here, right? So that's going to make the top negative. Now if up here becomes negative, what's going to happen down at the bottom? It's going to become what? Positive. Why does the bottom become positive? Well, if all the electrons get pulled up to the top of the electroscope, if all the electrons go up, that's going to leave the bottom positive. Is that easy enough? Now, if these metal foils down here are both positive, if they're both positive, what's going to happen? They're going to separate apart. Now let's do the same thing, but make it a negative rod. Okay, so let's make this a negative rod now. So instead of a positive rod, we have a negative rod. So if that's a negative rod, what's it going to do to the electrons that are hanging out up here? It's going to take them and do what? Shove them down. The electrons are going to get shoved down towards the bottom, which is going to make this now negative, like that, and the top is going to be what? Positive, but it's the same effect. It's the exact same effect because now both of these metal foils are negative. And if they're both negative, they're going to go and they're going to spread apart like that. Now, this guy over here, this is also an electroscope. So let's do negative rod again. So here's a negative rod. If you bring a negative rod near the top of the electroscope, what's that going to do to the electrons that are all up here? These electrons here are going to go where? They're going to get shoved down, which is going to make down here negative. All of this is going to be negative because it's all connected. And then the top of this will be positive, like that, because the electrons got pushed down. Now, if this bar right here and this bar right here are negative, what are they going to do? Are they going to come together or are they going to go apart? They're going to go apart, but they're going to go, this is going to go up like this. Does that make sense? Now, having done this, can you use an electroscope to determine charge, plus or minus? If I take this and charge it up, right, charge, 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 will the electroscope tell me if this is a positive or negative charge?
No.
No, because it's the same effect both ways. You know, the gold over here, the gold foils are going to separate, but they separate whether they're positive or negative. So can you use an electroscope to determine if something's plus or minus? Yes, if, so this is the final screen, I promise, if the electroscope is pre-charged. If the electroscope was previously charged with another known charge, it can be used to determine the sign of the charge. So let's just go through this. So here we have a previously charged electroscope. Okay, you take the electroscope like you charge it by conduction or something. You take a negative rod, touch it to it, bam, you charge the electroscope. So what would you expect to happen if you took a negative rod and put it near this previously charged electroscope? What's that going to do? It's going to take the electrons that are up here and do what? push them down even more. So notice it went from negative to even more negative. So what did those little those little metal foils do? They came apart even more. All right, now what if you had a positive rod? If the rod was positive, what's that going to do to these electrons that are down here? It's going to pull those electrons up, which is going to make these metal foils come closer together.